Okay, hello everybody and welcome to today's webinar, ML to the Max, using sensor fusion to increase accuracy and power on Sony Spresense with the SensiEdge Common Board. Today we are joined by Armagan Ibrahimi, Partner Solutions Engineer at Sony, and Owen Jordan, Developer Relations at Edge Impulse. During today's webinar, if you'd like to ask any questions, please post them in the Q&A box at the bottom and we will endeavour to answer those at the end of the session. With that, I will pass over to Owen.
Thanks, Louise. So I guess we can, have we got everybody now? Give it a moment or. Okay.
Yep, you're okay to go ahead. Yeah.
Okay, no problem. So today we've got the intro. After that, we're just going to have a quick overview of the benefits of Edge AI. I'm going to assume most people attending have a familiarity with Edge Impulse. So we'll keep this kind of quick and we'll hand over then to Sony, where we're going to get an introduction to the ecosystem and the changes that are happening to the CommonSense ecosystem from Armagan Ibrahimi. And then afterwards, we'll have a quick run through of Studio, followed by a quick run through of Sensor Fusion. And Sean Himmel has done a fantastic job of giving a run through of Sensor Fusion in a deep dive session, which is already on YouTube. So I'm going to keep that quite light as well. And then we'll have our challenge, which is predictive maintenance, and we'll try to walk through applying Sensor Fusion to that scenario using the SensiEdge CommonSense and the Sony Spresense. So Edge AI, let's have a quick overview, starting with the benefits of Edge ML. First of all, the types of innovation that we're able to apply at the edge are far greater than what we would have had in rule-based logic. And then some of the issues with Edge ML, with IoT, are addressed by Edge ML, such as privacy, power consumption, cost associated with network, and reliability, bandwidth, and latency. The types of models that we can build depend on the types of devices that we have and the class of device that we have, starting with our lower end can do single sensor classification and anomaly detection, followed by lower end MCUs, which can do sensor fusion and classification. And we can move up to all the way to GPUs, where we can do more complex video classification. And briefly touched on this at the first slide. This is a complete paradigm shift from traditional embedded programming, where we apply some rules to the input data, the input that we get from sensors. And we can do things like thresholding, where today's example would be VOC. If we go beyond a certain threshold, then we can have, I think it's an LED that's being flashed here in this example. Whereas with machine learning, we can apply we can start to predict outcomes based on inputs from sensor data. And machine learning is broadly broken into three categories: supervised learning, unsupervised learning, and reinforcement learning. Today, we're mainly going to be looking at supervised learning, where we'll do some classification, and we'll do a small bit of unsupervised learning, where we try to apply anomaly detection. So embedded machine learning, if you want to build your own tool set to do embedded machine learning, you need to think about your edge device, collect your data from it, design your model, test your model, and deploy it. And we also add processing features, where we can apply digital signal processing to extract features from your input signal. Here it's a speech saying yes, and then we can pass that to the neural network, our model, and get a confidence score such as 9.91 here for yes, and we can do something with that when we build our embedded solution. So now I'm going to give a handover to Armagan, and she will give us the Sony Spresense overview, starting with the Spresense. Thank you. I'm just going to stop sharing my slides for a moment.
Excellent. Thank you, Anne. Let me just bring up my slides here. Okay. So can you see my slides now?
I can.
Okay, perfect. Hi, everybody. Thank you for joining our webinar. Thank you, Luis and Owen. I'm covering the section for Sony's Spresense. In this section, I'm going to cover what is Spresense, how you can develop with it, and then I'm going to touch a little bit on CommonSense board and also Edge Impulse partnership that we have. First, let's talk about Sony's Spresense. Sony's Spresense is a microcontroller. It has 6 ARM cores and 156 megahertz of clock. Right there, you can see the Spresense has powerful processor. But another good thing about the Spresense is you have all these processors. Also, you have very low power. So if your application needs that many processors and also low power, probably Spresense is a good and suitable microcontroller for it. Look at the right side of my page here, slide. I want to highlight these features for you. So I told you this is very low power, and we are using the technique FD-SOI for maintaining this low power in Spresense. Spresense has high resolution audio, and GPS is already integrated in the board. So audio sensitive applications, like we have some examples that you can put Spresense in the trunk of tree and listen to the insects when they attack the tree, for example, or put it in the factory and listen to machineries. Or other applications that it needs high resolution audio, Spresense is a suitable board for it. And then GPS is already integrated, you don't need antenna, and you can create applications like drones, logistic, and those kind of applications that you need to cover find out where the location is. And the GPS is a global navigation satellite system, so it covers GPS, GLONASS, QZSS, and other places in the world. Before I move on to the next slide, I would like to talk about like memory and other accessibility to Spresense. If you look at the left side of this page, you see we have 1.5 megabyte of SRAM, we have 8 megabyte of flash memory, and if you need to access the digital I/O, you have access to GPIO, SPI, I2C, UART, and PWM. If you need to access the analog inputs, we provide 6 channels, and that is 3.3 volts. For audio, I said this is high resolution audio. You have 8 channels, which is digital, and we have 4 channels for analog. Also, you can access the stereo speaker. We talk about GNSS, global, and GPS and others all around the world. And other accessibility on the board is a camera interface that you can slide the camera right in. You have the SD card access, and also you can access the I2S. So this is the spec about the Spresense. Let's look at the components. We have, please look at the left side of this slide. So I have 3 components here. The middle one is the main board. Main board, it has 2 chips on it, which I'm going to explain what is in each of those chips. So main board is this board, first of all, everything is the production board. Main board is all you need. If you see the extension board or camera board or others here, is just to help you to build your prototype faster. And all of these boards are production boards. So you have the main board, you have the extension board. What is this extension board for? You have, for example, access. You can put your headphone in, or you can put other Arduino shields on top of it. And it makes it very easy to do prototyping without stuttering. So you just stack the boards on top of each other. And then for the camera, we have 2 cameras. One is the 5 megapixel camera, and the other one, which is kind of came out last year, is the HDR camera, is more light sensitive for night vision and outdoor applications. And to add connectivity, we have the LTE extension board, which is a Cat M1 narrowband IoT access. Let's talk about this main board. Main board has 2 chips on it. These 2 chips has been used in smart Xperia headphones, and each of these chips, they have different functionalities. For example, if you look at the CXD5602, you have low power GNSS functionality covered in this one. Or if you look at the other chip, you have the power management, which is available in this chip. If you need to get any of these boards, our main distributor is Framos. We also work with Adafruit and Mouser. Also, you can you can buy these boards. Let's see how, when I say fast prototyping, what do I mean? When we say fast prototyping means, okay, I have the main board here. I can put other boards, which can be my add-on boards or connectivity boards like Wi-Fi on top of Spresense. You don't need to do any sudden, just stack them all over on main board. And then also for extension board, I told you the extension board that you can get the audio out or put Arduino shields on top of it. And we have extension board and we have a portable player. The new thing for this webinar is we have a sensor add-on called CommonSense board, which me and Owen, we are going to cover a little bit more about it and tell you what is the exciting thing about it. So this is about the fast prototyping. Let's talk about development with Spresense, or like what kind of programming language, how can I develop with Spresense? If you look at the Spresense structure, it has 3 sections. Let's start from the bottom. Bottom one is we have 6 processors. I told you we have 6 processors is M4F, and then on top of that we have the memory. So this part basically is your hardware. And then when you go the next level, the OS on top of this is Nutex. So Nutex is supporting our GNSS, video, and others. Also, you can we have support for TensorFlow at this level. So you can write your programs with using this level, or you can go one level up, which if you want to use Arduino, these are the libraries that we support, like LTE, GNSS, and others. So we have Arduino also. We also work with third-party companies like Python. Edge Impulse is providing ML for our board, and Zernet and MicroEJ. So this is just to give you an overview how you can develop with Spresense. What I suggest is when you start with Spresense, go with Arduino, learn like what you expect, like connect the camera, see if you can take pictures, and then move to SDK, because here you have all the support and libraries available. Let's wrap up here and then move on to Edge Impulse and others quickly. So and Spresense is open source. You can access the schematic, you can get the BOM, and you can get the design guidelines to build your own board. So this is just an open source software to accelerate open innovation. To just give you an idea, for IT applications, you need a processor, you need a bunch of add-on boards, and then you need ML, you need connectivity. And then the good thing about Spresense is it has 6 ARM cores. You can do edge computing. So taking advantage of edge computing and sensor add-ons, and just have the camera already there, and high resolution audio, it makes the Spresense suitable for IoT applications. For Edge Impulse is our partner, and then I told you we have support for TensorFlow. But if you are not expert in data science, this tool is amazing. Like, it's very fast. In 5 to 7 minutes, you can create your model. Let's talk about Edge Impulse. Edge Impulse, as Owen said, you can get your data set, you can label them, and then you can train your model. When you generate, you can train your model, and then you can generate your model, deploy it on Spresense, and then run it on Spresense, and for example, to do some recognition. So this is the benefit of very fast for ML, and this is what our partnership is about with Edge Impulse. The other good thing that is happening right now, I told you we have a sensor add-on board, which is CommonSense board from SensiEdge. This is a partnership between Edge Impulse and SensiEdge that they are creating this amazing board. This is sitting right on top of Spresense. It has 10 environmental sensor in one board. So this is amazing to target applications that Owen is going to talk about some X-ray application later on this presentation. So I just wrap up my talk here. Let me see if I can move forward. And Owen is going to talk about the next section, which is the CommonSense board. Thank you so much. I'm just transferring.
Thank you, Armagan. And I'll just try to share my screen now. Here we go. So yeah, Spresense overview. And now let's take a look at the CommonSense. So I have the CommonSense here, and when you get it, when it's available from the 28th of July from Mouser currently, you'll be able to order your CommonSense, and it sits, as Armagan said, just above the Spresense. And we need the daughter, we need the main board as well for this, and with a SD card to be able to run the CommonSense. And the CommonSense just sits above the main board, the Spresense, and we install our firmware, specific firmware for the CommonSense, which you can get from our documentation page. And that will give you access to all of the sensors that Armagan has mentioned. And today we're mainly going to be looking at the air quality sensor, the SGP40, where we're going to try to detect some VOCs, which are volatile organic compounds. And so the way we see the CommonSense as well is it's got our name on it here, and we partnered with SensiEdge to develop it to give you access to an array of sensors that will complement the existing Sony Spresense ecosystem to use for sensor fusion examples. So I'm going to give you a quick overview of the studio, as I said, just very quickly. So Edge Impulse Studio is your UI to interact with Edge Impulse for building your impulses, we call them, because they include more than just the model. They also include digital signal processing, and we have custom firmware and drivers for our supported boards, which you can deploy to your board with the click of a button and the running of a script. And we are royalty-free business model, so it won't impact your bill of material costs, and your IP, anything that you develop with us belongs to you. There's no black boxes here, and there's total expandability. And on our enterprise tier as well, as you grow your model and your solution, we can offer more features as well to you. So in Studio, you can collect your data from any sensor. Here I'm collecting data from my VOC sensor from the CommonSense. And you can see I'm collecting. We'll suggest to you as well the kind of training and test split that you should have. Recommend 80-20 split, and this is pretty close here. And we recommend collecting about 8 to 10 minutes of data minimum. And then when you're designing your impulse, it's very user-friendly. Click add a processing block. There'll be a star next to the one that we think will you will need to associate with your project, and the same again for your learn block. And we applied advanced digital signal processing in this processing block, and this was developed by our digital signal processing engineers, and there's a lot of great suggestions here for all of the default settings. And as well as getting your initial model set up during the design process, this is an iterative process that we can come back to later, where we have some auto ML steps that will help you with tuning and refining your impulse. And then we have a testing phase where we can come back to the 20% that we reserved to run our built model or impulse against and classify this reserved portion. And finally, then we come to our deploy stage, where we can build our custom firmware, and you can see here our Spresense and CommonSense and how it will appear when it comes to the very familiar deployment stage, if you're already an Edge Impulse user. So now let's get on to the challenge for today. The challenge is trying to do predictive maintenance. Typically, predictive maintenance, we look at things like motors. The vibration on a motor starts to vibrate more, so we can use our inertial sensors like our accelerometer and our gyroscope to start to assess the vibration of that motor and see when it will break down. In this example, we have a challenge of a printer which has some motors in it, and additionally there are some volatile organic compounds, or VOCs, that can leak from a printer once it gets into a poor state. And I just have a quote here as well from the EPA on indoor air quality, which validates this about VOCs. Here we can see the HDR cameras also sitting on top here. And now let's get on to our solution. So our solution is applying sensor fusion. And sensor fusion is the combining of multiple sensors to input to build our model or train our model. And you can do this with different types of sensors or similar sensors. So the likes of stereoscopic cameras, you could have multiple cameras, or positional audio, you could have multiple microphones. Here we're using the VOC sensor and the inertial sensor to combined build a model that can predict when our printer is going to get in a bad state. So sensor fusion, you can see here the inertial and our gas sensor as an input, and this is the accuracy that I was getting during testing. With my, I have a fan and I have a fan to simulate the motor movement, and I have just a simple touch-up can for a car, which is high VOC varnish. So let's get into the demo here. So to start with, we have updated our Spresense documentation to include the CommonSense firmware, and the steps are very familiar for flashing your firmware. If you've followed the steps previously, you just need to run the new firmware and install that on your Spresense. Then I will go to my terminal here, where I can kick off my daemon to connect my device. Of course. What I will do here is I'll go to the dashboard and grab my key. My Spresense is connected. Let me see this. Just make sure that you've got your Spresense lined up, and you can see where there's a gap here for the camera that you'll be able to use to line up. Okay, so now I'm connected to my project. If I come here to devices, I can see the new sensors that are connected here. And I can go to data acquisition. What I've done here is I've collected data for the leaking printer condition, which is the fan on and the VOC exposed, which is my varnish. And then I have a nominal condition, which is just my fan on. And you can see, actually, one recommendation here is to collect your nominal state first and your idle state first. Because if you collect your leak state first, it's very hard to clear out the VOCs from your room. And I only just got this board on Monday, so pretty much yesterday I had to try and figure out how to clear out my office for the gas, and I was trying to build some of this outside. But today, starting with the nominal condition and the idle condition, I was able to build it. You can see here, I built it from scratch, started collecting data at about 3 p.m. and finished around 4. So yeah, about an hour, I guess, an hour possibly to build the whole model here. Collect my data. I'm going to gather more data here. I'll just do data acquisition here. So I've got my CommonSense. I'm not going to do leak. I'll do a idle, because it's just sitting on my desk. So here we can see all of the different sensors that we have. We have a lot of sensors here to select from, and almost every combination that you can imagine. So right now we're going to use our inertial sensor, which is a combination of the accelerometer and the gyroscope, and our gas sensor. And you can use a sample length here that you think appropriate. The maximum is about 13 seconds, which is 13,000 milliseconds here. So I'm just going to select, I'm going to get 1,000 here. I think will be enough just for demo. I'll start sampling. So now if I go back to the terminal, I can see I'm uploading data, capturing data and uploading it to my ingestion API. And it's uploading as training data. You can collect everything as training data and then take our suggestion here to split it between the 80/20. Okay, so that's our data collected. Now I'm going to move on to the impulse design here. So for the impulse design, we recommend using the spectral analysis here. And if I create a processing block here, you can see that the spectral analysis is great for analyzing repetitive motion, such as that from accelerometers, like the one within our inertial set here, which is our gyroscope and our accelerometer. So I use that. And you can see here we've got stars recommending the types of block that are associated with your input here. And then for classification, for our learning block, we're going to go with classification, where we're going to try to learn patterns from our data and apply this to new data. We're also going to try to do anomaly detection here to try to signal if we have any new inputs that we didn't anticipate. And so the order that you create them, you create your processing block, and then the spectral features that are fed from your processing block will go to your classification block. You can see here idle, nominal, and leak. And also our anomaly score here will get our spectral features. So we save our impulse, and then we can go with the default parameters here and save the parameters. And then you can see the features that are generated here. We've got idle, and we've got good separation here between idle and nominal. And then if I move here, we've got our leak here as well. It's quite close to our nominal. But, okay, we've got some separation here. We can see the on-device performance that we're getting. So it's going to take about 19 milliseconds to run this DSP block and consume 8 kilobytes of RAM. Now our classifier, which is our neural network, and we can see here that we're getting an accuracy of 97%, where we're able to detect our idle state, our nominal, and our leak. And I've made this project public as well, so you can, when you get your CommonSense, you can try to validate this as well, and you can run it, or you can clone it and adapt it as you want. And then for our anomaly detection, you can see our The settings here that I've used are the RMS value for the accelerometer, the gyroscope, and the VOC level. So we can see then that the clusters that we have here and anything that appears outside of these should appear as an anomaly when we try to classify our new input. You can also run the Eon tuner once you've designed your impulse, and that will help you to tweak and adjust all of the settings in your impulse and try to get better accuracy or more RAM or ROM optimization for your model if you want to do more things like work with connectivity to a IoT network, or if you want to do some other logic in your embedded program. And we can retrain our model. I'm going to do live classification here. I'm going to see if I'm able to get my idle state to appear. So I'm going to connect with web USB here. I can connect to my Spresense. Okay, I do have my firmware on here, so see if we can connect here again. You know what? I need to kill my daemon here. And now I should be able to see it here. Connect. Start sampling. Okay. I'm just going to disconnect and reconnect here. And okay. I can use an existing example here. Here we can see that we're getting our leak detected for our nominal condition. And we've got an anomaly here. So we could benefit here from more training data, I think. But yeah, nominal is getting detected here. Okay. So we can classify our reserved portion of our set here as well, if we classify all. Okay, so we're getting 60% accuracy on our test set here. And again, I've made this project public. Now let's get to the deployment section. I'm going to build my firmware. And I'm enabling the Eon compiler here, which will save up to 50% memory, and it's going to cut out all of the extra bloat that we don't need. Okay, so I unzip this in here and run my, oh, sorry, I built the C++ library. Okay, so I need to obviously change that and search for the Sony Spresense. It's my device here. Enable the Eon compiler, build. You can see what we're getting here. So how much space we're going to be using here versus our unoptimized. So we're making some save-ins here on the flash. 60% savings total. That's great. And this will just take a moment to build all my firmware and bundle in the model and into our impulse that's able to connect to all of the sensors that are on your Spresense and your CommonSense. And once that's ready, we'll flash the firmware directly onto the device, and then we'll do our run impulse and try to interact with the device and see what kind of scores we're getting. And I'll get my VOCs ready here. My fan. There's my let's flash that onto the device. Sorry, I can probably cut that fan off for a moment. It's pretty loud.
It's okay. We don't hear it, I think.
Oh, you don't hear the fan? Okay, I'll leave it on. So.
Not really. Yes. If you're okay with it, let it be.
Yeah.
So meanwhile, this is you're flashing this. I added 2 links. One is the one that you showed at the beginning, Sony's Spresense and Edge Impulse, and
Yep.
also the main page for Spresense in the chat if people want to look into it.
Okay, great.
Okay, continue.
Let me get that. So I think I must have bumped my device here. I'm just going to check for a moment. I'm glad I prepared most of this model already, because I'm getting struck by demo demons already. Okay. So I'm just going to disconnect the board here again. Reconnect. And select my serial. Yep, okay, that's looking better now. I think I must have bumped it just as I was moving it over to the fan. No, okay, great. Now we can simply run our impulse. Now we're connecting to the device, and it has our model integrated into the firmware, and it's running on the binary. Here we go. We're connecting to the serial, and we're predicting. Now it's recording the sensor data. Let me move this over to the fan. Okay, and we're able to see that we're getting we were getting a high score there for the leak. So yeah, I'm pretty happy with that. Okay. So let me move back to the slides and I'll turn this off. So I'm just going to move back to the slides now. What we did. So just let me know if you can see my screen.
Yes.
Okay, great. So yeah, the conclusions here, the Sony Spresense and the CommonSense together are able to do more advanced types of predictive maintenance scenarios that involve air quality, or indeed there are other sensor fusion examples that we could look at here, such as the one that Sean Himmel went through, where he built a complex version of the intelligent wand, and I'd advise following that along if you want to look at sensor fusion more and you want to get some inspiration for your Sony Spresense and your CommonSense. And I've also included a nice box here that you can use for your air quality type scenarios, with just some space for a screen, your Spresense and all of your connectivity, and also any additional sensors that you would like to add. You can also add, because we've added some support for the ADC. So there's other types of sensors like the ones that I've shown in the screen here that you can add to your ADC to further enhance your Spresense ecosystem. And that was about it that I wanted to go through here. And so limitations and a recap and where to get this SensiEdge CommonSense mouser is available from the 28th of July. And if you want to download and print this box, you can get that from Thingiverse and Own Edge Designs. And is there anything else that we wanted to do here? So yeah, if you want to go further, if you haven't already joined Edge Impulse, please do, and create your account. You can build your first model without any hardware. Within about 5 minutes, you can use sensors from your phone to get started. And then you can order your CommonSense and your Spresense, and you can follow along on our CommonSense docs and follow as well the sensor fusion documentation. And again, I highly recommend following the sensor fusion with Edge Impulse video from Sean Himmel on YouTube. And my project as well is the Studio Edge Impulse. Sorry, I'll share a link. Don't worry, that'll be in the video. You can join it. It'll be a public project that you can clone and do what you want with. Oh, some dogs outside. I hope we couldn't hear that there, but thank you for joining today's webinar, and I hope that we have got a bit of time for questions. And my name's Owen, if I didn't already say that, which I think I did. Okay, thank you.
Thanks, Owen. Thanks, Armagen. I have actually got a couple of questions that have come through. First one is, what is the maximum size of the AI model you can use?
So is that okay if I take this, Owen?
Yep, sure, of course.
Yes. For the maximum size of AI, Spresense has 1.5 megabytes of space. So if your model is something around 1 megabyte, that is what's suggested for Spresense. So Owen, if you want to add anything else from the Edge Impulse side, please do.
No, and I think that's a good target to start for.
Okay. We have another one here. What is the lowest power consumption in sleep mode?
This is, again, can I take this on? This is for Spresense, the lowest power consumption is 6 microamp. And also, I can also share a link for this if people are interested to look more into this, how this is possible. Just a second. I put it in the chat. And also we provide these slides, I think, to everybody. So we can also have a section for, oh, I think I put the wrong one. Sorry. Just, I included the link for Mouser, where you can buy the where you can buy the Spresense and the CommonSense board. I think this one is the guideline for the power consumption.
Great, thank you very much.
Yes. Sure.
Okay. Can I use data from sensors other than audio and camera as an input to my neural network?
Oh, I think I can take this one too. So Spresense has the camera that it comes 2 types of camera image sensor that you get with the Spresense kit, and also it has the high resolution audio. I think the question was, can we use other sensors, right?
Yeah, can I use data from other sensors other than audio and camera? Yeah,
sure. As Owen just talked about, the CommonSense board that is an add-on board that you put on top of Spresense. It includes 10 sensors, so that any add-on board for Spresense you can put on Spresense and collect data. It could be something like CommonSense board that it has like 10 sensors, or it could be just a temperature sensor, just one sensor, but you can connect other sensors to Spresense to collect the sensor data. I hope I answered that question.
perfect, thank you. And then one final question. Can I train my model on Spresense?
Oh, okay, yeah, I can take that one. So I guess unless you are able to, I don't believe that you would be able to. Typically what we do is that's what Edge Impulse is about. We train the model on the cloud, and then that model is bundled into the firmware, and you download that, and then either as a C++ library that you can build your own logic around, or as the Sony Spresense firmware, which you can then deploy to your device. So I don't believe that you're able to train on the Spresense.
That's correct. Spresense is not capable of building a model. Spresense is a microcontroller. So what you need to do, you need to use Edge Impulse, build your model, deploying on Spresense. As you mentioned, yeah, it has to be on the cloud tools like Edge Impulse to create your model, then deploy it on Spresense. Exactly.
Which is pretty crazy. I mean, to think about types of microcontrollers that people were using for very simple types of scenarios just a few years ago are now able to apply these types of models that were built on cloud infrastructure is quite crazy.
Yeah, I think the best, I mean, what I'm really excited about for Edge Impulse is, as I mentioned, like we are not all data scientists, and we want to develop our IoT applications, and there are different components in IoT applications. Okay, I have my MCU, I have my sensors. Now I need to build my model. So I either need to go deep down and learn TensorFlow, or come to Edge Impulse, as you did just in this webinar. You collect all of the data, you connect your board, you build the model, train it and everything, and deploy it on Spresense. And everything is GUI based and very easy to use. So I think Edge Impulse is a very good addition to Spresense ecosystem to help with, you know, building the model and make it so easy and fast. Like the first model that we had to just have one sensor, it was only 5 to 7 minutes. So that is amazing to be able to use Edge Impulse for IT applications. And
it's a very good way to build on your, if you're coming from an IoT background, to be able to build this types of solution that otherwise you would have been trying to enlist some kind of cloud solution that that you're streaming all of your private and personal information up to. Now you can do these types of these types of inferences on the edge of the network is crazy.
Exactly.
And as well, it is very easy as well for somebody coming from an embedded background or coming from an ML background to bridge the gap as well there. So if you do have embedded experience, but you want to learn about ML, then it's a great way to do that with the Spresense and Edge Impulse. But if you're coming from an ML background and you like to use Colab and Python tools, you can do that too. And you can integrate us into your workflow, and you don't need to learn about all of the types of deployment problems that you need to try to solve to get your model onto a device. Yeah, I think it's a great question.
Yeah. Oh, and also let's talk about this. Like now we have because the way that Edge Impulse is, if you have a hardware, like if you have a MCU like us, Sony, so it gets support on their Edge Impulse too. So you can, when you build your model, you can click on different type of device. You can choose your device, and now Spresense is fully supported on their Edge Impulse. CommonSense board is fully supported on their Edge Impulse, and now we have FOMO, we have sensor fusion, right? And then you said digital signal processing also for audio is these are kind of big. Like talk about a little bit of about FOMO. FOMO is amazing.
Yeah, so FOMO, yeah, thanks for bringing that up, Arm, again, because FOMO is object detection, which we can run on very low class of device. So you can run so the like very low powered devices can now run object detection, whereas we would have typically a number of years ago we would have only seen this happening on things like Raspberry Pis with OpenCV, let's say, or larger classes of hardware that are running on complicated servers. But now we can do this on a microcontroller that just a few years ago was being used for very simple logic. Now it's being pushed to the very limit through research and through advances as well in microcontroller development as well, where we've got these new multi-core microcontrollers that are also pushing the boundaries here as well with the research. So yeah, it's very interesting to be able to see the types of things that you were doing a few years ago that were very power hungry, now running for very cheap amounts of effort on a device that you can run in, let's say, a wildlife camera scenario. You can now do object detection on a device that could be remote in the wilderness that only fires up every couple of hours to run this object detection, which you couldn't do a few years ago. You couldn't have a server there, or Raspberry Pi with a massive battery pack. I don't think would have been, or like a single board computer wouldn't have been power efficient enough really back then.
Yeah.
To do.
It's amazing. And also at the end, when you create your model and everything, you can optimize it. You can make it smaller, because MCUs always struggle with memory space. So it's amazing to be able to optimize it and put things together and then deploy it. So this is an advantage of Edge Impulse. I want to mention fast moving objects, right? So is like the example for FOMO is when you are monitoring a beehive, I think. All these bees going back and forth, and they're really fast, but you can detect that, you can build your model. So I think we have an example with the new HDR camera, Spresense and Edge Impulse. I think we had, I think we have some links, if I can find it, I will post it or put it in the slides. Oh, we are talking too much. Louis, do we have any other questions?
No, that's all the questions for today.
I'm glad you brought up the HDR camera, because I just got mine and I'm looking forward to starting to build with it now that I've, so the next webinar I'm looking forward to getting to play around with the HDR camera, and very excited to have things that we can do with it. So
very nice. Thank you.
Thanks for joining us today, and thank you, Louise.
Thank you.
Thanks, Aman. Thanks, Owen.
Louise,
thanks everyone for joining.
Thanks everyone.
Bye-bye.
Thank you. Bye.